times x squared plus 1. What does this tell you about the intercepts? It's a cubic, so you'd usually expect it to have, like, 3 intercepts or something like that. But as you know, cubics don't have to have 3. They can have 2 or they can have 1. They can't have 0. I hope you can see why that is. But anyway, there's just one. Where? The origin, okay, comes from this part of the product, that factor, right? X squared plus 1, though, that's a bit interesting. As one of the factors, it tells us something useful. Namely that x squared plus 1, right, is never equal to 0. Never, ever, ever, ever. So, therefore, I'm not going to get any intercepts from this part, okay? So x equals 0, that's my only intercept. And it just so happens when you pop that back in, you get the origin, okay? So one intercept, if you were to plot some points, you would get this kind of shape. Ta-da! Okay, there's the graph. We were talking about one smooth line this morning, right? Well, there you go. Now, what can we use to describe this graph, okay? Well, we actually already have a lot of language to talk about it. Think about its gradient, okay? It's always going from bottom to top. So how could we describe this function? Yeah, it's increasing, and it's monotonically increasing, because it's always going up. It never turns around. There are no stationary points. And it never stops, right? So it's always increasing, okay? Let's go a little further and dig into this though, because it's not always increasing in the same way, okay? So what I want us to think about is, well, gradient, we get information about the gradient from the derivative, right? So let's work out that derivative. Okay, look at your first line, x cubed plus 1. So my derivative will be, good. Simple stuff, okay? Now you can see therefore why I have no stationary points on this graph. Because 3x squared plus 1, I'm actually going to graph that on. If you've got another colour on hand, you might like to do the same as well. What would this look like in relation to this graph? Well, it's got a y-intercept of 1, okay? And then the rest of it just sort of goes up like so, okay? So something like this. Okay, so I've got y, and I've got dy and dx on the same graph. Okay, so you can see because dy and dx, my green line, never hits 0. That's why there's no stationary points. Okay, but you can also see that this is not a constant line, right? The gradient does change. Okay, and in fact, well, how can we describe its change? Let's think about this. You can say its gradient is parabolic, but what does that mean for the original graph? Well, what I want you to do is, what's the biggest piece of paper I've got? It's not very big. This, no, both sides. Okay, I'm just gonna steal this. Yeah, okay, this will do. All right, I want us to focus on the left-hand side of the graph. Okay, so I'm gonna cover this whole lot. And have a look at it. Okay, this part down here, probably. Yeah. Oh, well. I'm probably removing part of the graph as I speak. But anyway, have a look at it. It's increasing. It is still monotonically increasing, but how would you describe? I mean, it's not increasing the same here as it is here, right?
At a decreasing rate.
Now, let me say that again. In fact, I might even jot it down, for which I'm going to... Oh, yes, yeah, I ruined it. There you go. And it's on a little bit. Hardly, actually. Let's put this down, because this is actually an important phrase. It's not the only way to describe it, but it's a good one. My one smooth line is destroyed. Oh, well. Okay, so over here, right? And in fact, you might even like to write down 4... x is less than 0, okay? The graph, or I could take y, right? Y of x, because it's a function, right? Is increasing at a decreasing rate. So you can see, if I went to the leftmost part of the graph, that is where the graph is steepest, okay? See here, right? And it gets shallower and shallower and shallower. It doesn't stop, there are no stationary points, okay? But its increase rate is slowing down, okay? Increasing at a decreasing rate. Now, what does that correspond to? You have a look at the green graph, right? The green graph tells you how much the blue graph is changing, okay? So you can see it's increasing. It's always increasing because the green graph is always positive. Positive, the sign of the first derivative is positive, so that's why it's always increasing. But as the derivative gets lower and lower and lower, that corresponds to the fact that this graph is slowing down, okay? So if you like, if this was like our apple, right? the apple is going up, but it's getting slower as it goes there. So if you actually were to record the speed of the apple as it goes up, okay, that speed is reducing, okay, sort of, which is what it was doing. You know, the pull of gravity was making it sort of slow down, okay. So for x less than 0, it's increasing at a decreasing rate. But if you go past the origin, the positive values of x, right, it's increasing at an increasing rate. Because you can see it's getting steeper and steeper and steeper. Okay? So if you thought of it like as a car, right? It's driving along at a certain speed, but then you're pushing the pedal down and it's getting faster and faster and faster and faster forever, which would be nice to have a car like that, but it doesn't exist, unfortunately. So, increasing at a decreasing rate and increasing at an increasing rate. Now, can you see what's going on here, right? In this first part, increasing, I'm talking about the first derivative, right? But then, I'm also talking about how the first derivative is changing. How the first derivative, dy dx, is changing. Now, how much something changes, right? That's the whole idea of what a derivative is, right? The first derivative tells you, the green line tells you, how much the blue line is changing, okay?